This is Team M4 submission for our rainwater harvesting system. Pictured below are the team members who made this presentation possible. Here is an outline of our presentation where we'll be going through the 6 main components, starting with context. The purpose of this project is to design a rainwater collection system for the rural parts of British Columbia. Specifically, we aim to introduce this system to strategic research companies that work in providing clean drinking water for small, rural, and First Nation communities. Our team strategy can be focused into 3 pillars, namely community engagement through stakeholder consultation, simulation, and rigorous testing to ensure that our system is reliable, and thirdly, a detailed analysis of the project, including environmental impact, as well as user satisfaction curves to ensure we provide a comprehensive design. Our main design criteria were obtained after rigorous consultation with our primary stakeholders, who were the Van Ander residents and the Water Board of Trustees. After the consultation with these groups, we found out that the 3 main needs were that the system needs to be accessible, reliable, and cost-effective. Our design process is derived from the APSI 100 framework, and we focus mainly on stage 4 and stage 5, as the previous stages were covered in the module 6 of this course. Key assumptions in this project were, firstly, that the data provided to us was accurate and that there would be no significant changes in climate which would affect the performance of our system. However, we did test our system and included some of this variability to ensure our system was robust. Secondly, we also assumed that there would be no major equipment failure that would cause a big problem in the project. We conducted an environmental risk analysis that led us to discover 3 main risks in our project. The first one being water quality, where we found that water may contain algae, bacteria, and toxins, and that the use of an ozone purification system could get rid of this. The second were medium risks, which were related to solar panel production and the impact our system would have on natural habitats. Here is an illustration of our rainwater collection system showing the main components. In the next parts of our presentation, we'll go into a depth discussion on why we chose each component and how this creates the optimal solution that meets our user needs. The first component is the storage system and its placement. This slide shows our final positioning and configuration for the storage system. The main things we considered were finding a suitable trade-off between low cost, maximum elevation with minimal piping. Our final choice requires 145 meters of piping, which was the best we could get for the desired outputs our users need. Secondly, we had to select a pump. We were given 3 pumps to choose from, with increasing power from left to right. Pump C, although it satisfied the minimum threshold value, was an overkill, as we could achieve the same performance with Pump B, which was cheaper and at a reasonable cost compared to Pump C. We then conducted a studio experiment during class to calculate the coefficient of friction, and this would be useful in determining which components to use in the future parts of our project. This data allowed us to predict losses for our system using proportionality. The filtration system makes use of all 3 filters. This is because it will result in less frequent maintenance in the long run. However, the disadvantage of this is that it is more expensive to set up and repairs can be quite costly. Our UV light system uses the 36-watt lamp because this maintains the minimum flow rate and is cost-effective, as a 50-watt lamp will just result in a marginal increase in user satisfaction. Here are the options we had for disinfection systems. Our key findings from evaluating our disinfection options were that chlorine, although more expensive, has associated risks in terms of health and the environment, and also has higher maintenance. Ozone, although requiring more maintenance, results in more safe and clean water for our users, and this outweighed the relative ease of low maintenance provided by chlorine. We then had to choose between a solar-powered system or a diesel-powered system. And to do this, we considered both options and evaluated them based off cost required maintenance, and environmental impacts. After depth analysis, we found that solar was cheaper, although had slightly worse performance than diesel, had less greenhouse gas emissions, low environmental risks, and required slightly more maintenance. However, it is sustainable in the long run, and we decided to proceed with this option. The next step was to choose a solar panel. We found out that HES260 was a better panel as it was affordable and provided the optimal amount of energy that our system required. As mentioned earlier, we used a spreadsheet to model our system, where we tried different alternatives. Here are the top 3 alternatives that we found. The satisfaction was found by fine-tuning different parameters within the configurations. As can be seen, option 1 is the highest, and as a result, this was our final system. Below, you can see the final parameters for our chosen system and the previous illustration, reflecting the position of the different components. Our final project has the following features: a consumption of 520 liters a day, negligible environments and health risk, on-demand flow rate of 19 liters per minute, very low maintenance, and high reliable days. Our total project cost was estimated to be $55,000. The system performs very well, and the major cost in the project lies in the tanks and piping, which is unavoidable. In future, we could use more batteries to reduce the number of unreliable days where we have to import bottled water. For the justification of our final system, we considered our strategic priorities, where we saw that our chosen system was reliable, cost-effective, had high user satisfaction, and was accessible. Thank you for listening, and we hope that our system meets your needs, and we look forward to working with you in the future.